Dr. Engineering Thermodynamics, Assistant Professor. SRM Institute of Science and Technology. Unit 1, First Law of Thermodynamics 9 hours. Basic concepts, microscopic and macroscopic point of view, path, and point functions. Intensive and extensive, total, and specific quantities. System and their types. Zeroth Law of Thermodynamics, thermodynamic equilibrium. First Law of Thermodynamics, first law for a closed system undergoing a cycle, concept of internal energy, change of state. Energy and work transfer in closed systems, PV diagram, PMM1. First law for an open system, conservation of mass, energy, steady flow energy equation. Applications of SFEE to nozzles, diffusers. Types of turbine, compressor, boiler, pump. Heat exchanger and throttling process. Unit 2, Second Law of Thermodynamics 9 hours. Limitations of the First Law of Thermodynamics, Introduction to heat reservoirs, sources, and sinks. Heat engine, refrigerator, and heat pump. Thermal efficiency of heat engines, COP, Second Law of Thermodynamics, Kelvin-Planck statement, Clausius statement, and their equivalents. Reversible and irreversible processes, causes of irreversibility. Carnot theorem and corollary. Absolute thermodynamic temperature scale. Carnot cycle and its performance. Unit 3, Third Law of Thermodynamics and Entropy 9 hours. Limitations of Second Law of Thermodynamics. Explanation of the concept of entropy. Clausius inequality, TS diagram. Entropy change for different processes. Principle of increase of entropy, PVT behavior and properties of ideal gas mixtures. Dalton's law of partial pressures, Avogadro's law. Gibbs-Dalton law, enthalpy and specific heat of a gas mixture. Maxwell relations, TdS equations, difference and ratio of heat capacities. Energy equation, Joule-Thomson coefficient, Clausius-Clapeyron equation. Entropy change of ideal and real gases. Isentropic efficiencies of steady flow devices. Exergy high and low grade energy. Available and unavailable energy of a source and finite body. Unit 4, Air Standard Cycles 9 hours. Otto cycle, diesel cycle, dual cycle. Indicator diagram. Air standard efficiency, mean effective pressure. Brayton cycle, effect of reheat, regeneration and intercooling. Isentropic efficiency of turbine and compressor. Equivalent Carnot cycles. Stirling and Ericsson cycle, Humphrey cycle. Unit 5, Basic concepts, heat transfer and combustion 9 hours. Modes of heat transfer: conduction, convection, and radiation. Governing equations for conduction. Newton's law of cooling, free and forced convective heat transfer, ablative heat transfer. Heat exchange due to radiation, fundamentals of mass transfer, Fick's law of diffusion, fundamentals of combustion and dissociation, simulation of heat transfer and combustion processes. Unit 5, Basic concepts, heat transfer and combustion. Modes of heat transfer: conduction, convection and radiation. Governing equations for conduction. Newton's law of cooling, free and forced convective heat transfer, ablative heat transfer. Heat exchange due to radiation, fundamentals of mass transfer, Fick's law of diffusion, fundamentals of combustion and dissociation, simulation of heat transfer and combustion processes. There are three modes in which heat may be transferred. A. Conduction. B. Convection and C. Radiation. Conduction refers to the transfer of heat between two bodies or two parts of the same body through molecules which are more or less stationary. In liquids and gases, conduction results from the transport of energy by molecular motion, and in solids it takes place by a combination of lattice vibration and electron transport. In general, good electrical conductors are also good thermal conductors. The following are the assumptions on which Fourier's law is based. 1. Conduction of heat takes place under steady state conditions. 2. The heat flow is unidirectional. 3. The temperature's gradient is constant and the temperature profile is linear. 4. There is no internal heat generation. 5. The bounding surfaces are isothermal in character. 6. The material is homogeneous and isotropic, i.e., the value of thermal conductivity is constant in all directions. Convection heat transfer occurs because of the motion of a fluid past a heated surface. The faster the motion, the greater the heat transfer. The convection heat transfer is usually assumed to be proportional to the surface area in contact with the fluid and the difference in temperature of the surface and fluid. Q equals hot, TWTF. Newton's law of cooling. Radiation heat transfer is the result of electromagnetic radiation emitted by a surface because of the temperature of the surface. This differs from other forms of electromagnetic radiation such as radio, television, X-rays and gamma rays, which are not related to temperature. General heat conduction equation in Cartesian coordinates. Where Q is the rate of heat flux in W/m2. dt/dx is the temperature gradient in x direction, and K is the constant of proportionality, which is a property of the material through which heat is being conducted and is known as thermal conductivity. The negative sign is being used because heat flows from a high to a low temperature region and the slope dt/dx is negative. For a finite temperature difference, T1, T2, across a wall of thickness x. If A is the surface area normal to heat now, then the rate of heat transfer. Resistance has an analogy in the flow of electricity. Ohm's law states that the current, I, flowing through a wire is proportional to the potential difference, E, or where 1/R is the constant of proportionality, and R is known as the resistance of the wire, which is a property of the material. Since the temperature difference and heat flux in conduction are similar to the potential difference and electric current respectively, the heat conduction rate through the wall may be written as and the rate of heat flow. Again, T1, T2 equals Q, R1 equals Q. X1/Ca, from which T1 can be evaluated. For conduction through resistance in parallel, the total resistance R is given by and the rate of heat flow. Let us assume that the inside and outside surfaces of the cylinder are maintained at temperatures T1 and T2 respectively, and T1 is greater than T2. We will also assume that heat is flowing, under steady state, only in the radial direction, and there is no heat conduction along the length or the periphery of the cylinder. The rate of heat transfer through the thin cylinder of thickness dr is given by heat conduction through a cylinder. Conduction of heat through hollow sphere. Heat transfer through a composite plane wall with inside and outside convection. Ablation is a means of
transfer.
thermal protection based on physicochemical transformations of solid substances by convective or radiation heat flow. Advantages: heat absorption and dissipation. Exceptional thermal insulation. Weight savings. Availability. Resistance to mechanical and thermal shock. Design simplicity and flexibility. Low cost. Limited heat transfer, susceptibility to high mechanical forces. Service life is time dependent. Applications: aerospace engineering, furnace refractory manufacturing, thermal manufacturing, hypersonic atmospheric entry. Ablation is a means of thermal protection based on physicochemical transformations of solid substances by convective or radiation heat flow. Advantages: heat absorption and dissipation. Exceptional thermal insulation. Weight savings. Availability. Resistance to mechanical and thermal shock. Design simplicity and flexibility. Low cost. Fundamentals of combustion and dissociation. Fundamentals of combustion and dissociation. Fundamentals of combustion and dissociation. A general chemical process where molecules break down into smaller components, such as atoms, ions, or radicals. Dissociation is a reverse process that occurs at high temperatures, breaking down products like CO2 and H2O into smaller species like CO, O and O. Process. It is the reverse of association or recombination. For example, a simple dissociation is an acid splitting into a proton and a negative ion when dissolved in water. Energy. Dissociation is an endothermic process, meaning it requires the input of energy. High temperature effect. At the extremely high temperatures of combustion, often above 2000 K, some of the primary combustion products, CO2 and H2O, begin to dissociate. Reaction. These products break down into intermediate species like carbon monoxide, CO, oxygen, O, and hydroxyl radicals, O. At the extremely high temperatures within a rocket engine's combustion chamber, 2500 to 3500 K, the exhaust products do not remain as stable molecules. Instead, they can break apart, or dissociate, into more fundamental atoms and smaller molecules. Effects of dissociation on rocket performance. Reduced combustion temperature. Mechanism. Dissociation is an endothermic process, meaning it absorbs energy, heat, during combustion. This absorption of heat lowers the overall temperature and pressure within the combustion chamber. Impact. Lower temperatures and pressures lead to a lower specific impulse and a reduction in the overall energy output and performance of the engine. Recombination in the nozzle. Mechanism. As the exhaust gas expands and cools while moving through the nozzle, the dissociated components ideally recombine back into stable molecules. This recombination is an exothermic process, releasing the energy that was absorbed during dissociation. Impact. A perfectly shifting equilibrium flow where recombination keeps pace with the expanding gas maximizes the thermal energy converted into kinetic energy and thrust. Fundamentals of combustion and dissociation. Adiabatic flame temperature is the maximum temperature reached during a combustion process where all the heat released is used to heat the combustion products, with no heat lost to the surroundings. It is a theoretical value that assumes ideal conditions, such as a perfectly insulated chamber and complete combustion, and is higher than the actual flame temperature. Factors like excess air, heat loss, and incomplete combustion lower the actual flame temperature. Specific impulse, ISP, is a measure of rocket engine efficiency, indicating how much thrust is produced per unit of propellant consumed. The specific impulse is the ratio of thrust to the weight flow rate of the propellant. The specific impulse is also equal to the engine's effective exhaust velocity. Equals specific this means impulse. That a faster exhaust velocity leads to a higher specific standard impulse. Gravity equals 9.81 m/s superscript 2. It is often expressed in seconds and is analogous to miles per gallon for a car, where a higher ISP means the engine uses propellant more efficiently. A higher ISP means less fuel is needed for a given amount of impulse or change in momentum. If a rocket engine has equals 300, it means, for every kilogram of propellant, the engine could produce a thrust equal to the weight of 1 kilogram for 300 seconds under Earth gravity. Engine fundamentals coking is the formation and dissociation carbon-based deposits caused by the breakdown of oil or fuel at high temperatures. Coking in rockets is the thermal decomposition of liquid hydrocarbon fuels, like kerosene or methane, into a solid carbon deposit, coke, on the interior walls of engine components. Thermal decomposition of liquid hydrocarbon fuels involves breaking them down into simpler substances using high temperatures, often between 450–800 C. This process, also known as cracking, produces a mixture of gases like hydrogen, methane, and ethylene, along with liquid products such as smaller hydrocarbons and aromatics. Engine coking is the formation of black, carbon-based deposits caused by the breakdown of oil or fuel at high temperatures. Coking in rockets is the thermal decomposition of liquid hydrocarbon fuels, like kerosene or methane, into a solid carbon deposit, coke, on the interior walls of engine components. This occurs when the fuel is used for regenerative cooling and is heated to high temperatures, leading to a decrease in heat transfer, potential engine damage, and reduced lifespan, especially in reusable engines. Regenerative cooling is a method used in engines, especially rocket engines, to cool the combustion chamber walls by circulating a propellant, fuel or oxidizer, through channels in the walls before it enters the combustion chamber. This process cools the engine's hot walls and simultaneously preheats the propellant, which can then be injected into the combustion chamber to contribute to thrust. Simulation of heat transfer and combustion processes involves using computational fluid dynamics, CFD, to model the complex, coupled phenomena of heat generation from combustion and its subsequent transfer through fluid and solid domains. These simulations are crucial for optimizing and designing systems like engines, boilers, and furnaces, often using software like MATLAB/Simulink or specialized CFD packages. Researchers simplify models by using the rate of heat release, ROR, to represent combustion, which reduces computational costs for heat transfer calculations while maintaining accuracy for overall results. Key simulation of heat transfer and combustion processes. Coupled physics. Simulations must solve for multiple interacting phenomena simultaneously. Real-world systems are inherently complex, involving different physical, chemical, or social processes that are interconnected and influence each other in real time. Fluid dynamics. Modeling the flow of gases and particles, including turbulent and swirling flows. Heat transfer. Incorporating conduction, convection, and radiation to accurately represent how heat moves through the system. Combustion. Simulating the chemical reactions between fuel and oxidizer, including reaction kinetics and species transport. Combining the modes. Synergy in real systems. In most real-world applications, multiple modes of heat transfer occur simultaneously. For example, a hot engine block will conduct heat to the surrounding air, but the air movement will carry heat away via convection, while the block also radiates heat to the environment. Accuracy and complexity. Accurately modeling these combined effects provides a far more realistic and precise representation of the system's behavior than considering any single mode alone. This is especially important for applications like thermal management, energy efficiency, and climate modeling. Benefits of accurate modeling. Optimization allows for the optimization of designs to improve thermal performance. Safety helps in designing systems to prevent overheating. Sustainability contributes to energy efficiency by reducing energy waste.